right, so we're going to jump into modeling with optimization, which is one of the most common ways calculus is used in the real world. And these come up in scenarios where you're trying to find the biggest or the smallest or the cheapest or strongest or prettiest thing that you're trying to optimize. And the only thing we have to keep in consideration is a lot of times there are some type of secondary constraints or limiting factor that are also at play, usually with the feasibility of what's possible. All right, so these problems are going to feel a little bit like related rates where, yes, there's a lot of steps to it, and they're application problems, but they're a little bit more straightforward in a lot of ways. So first you're going to read the problem and draw a picture, and then state what you're trying to optimize and what equation you need to use to be optimized. So that's how it's very much related to how we start related rates problems. Then you're going to state any constraints and write a secondary equation involving the constraints if it's necessary. So a lot of times for these problems you'll have two different equations, and the constraint one is the one we use to kind of like rearrange and substitute in for an unknown variable in the optimization equation so that we're working with less unknowns. You're going to, basically step 5, then you're going to simplify after you plug it in, derive it, because remember if we're maximizing or minimizing something, those are essentially looking at critical points. So you're going to find the first derivative of your function, find your critical points, consider endpoints, because this is kind of like what we do with the candidate test, where we test the critical points and the endpoints, and then we choose from that whatever the max or min may be. Let's see, answer the question in complete sentence. Units are important, and yep, all right. Let's jump into example 1. All right, so two positive numbers have a sum of 60. What is the maximum product? So that's your giveaway that it's an optimization problem of one number times the square of the second number. Okay, so the very first thing I'm always going to ask you to do is write down what it is you're trying, I can't spell, optimize, that you're trying to optimize. And in this case, we want the maximum product. So we're trying to optimize a product. Okay, and in this particular case, we want a maximum product. All right, and so we're going to write an equation that we're going to use for this optimization. And in this case, they want the product of one number, which we'll call x, times the square of a second number, and we don't know what it'll be, so we'll just call it y, and it's the square of it. So that is my equation I'm going to optimize here in a minute. The problem is when we do critical points and we're looking at the derivative for where it could be 0, we're always in terms of one variable. We don't do this with implicit differentiation. So it's a problem that I have two different variables. So usually that means there's some sort of constraint floating around that's going to allow you to make a substitution. And in this case, the very first sentence is where we'll locate that. So the constraint is going to be the two positive numbers that we don't know, x plus y, have a sum of 60. Okay. So what I'm going to do now is I'm going to solve this for either x or y, it doesn't matter. That's usually a personal preference, and I'm going to substitute it in for that other variable. Now in this case, usually we're working with x's. However, when I see something being squared, I don't particularly want to plug something in and then have to deal with that. So in this case, I personally think it's easier to substitute in for x. So I'm going to solve for x here, and I get 60 minus y. So now I'll be able to write it in terms of x. So I'll go ahead and write p of x. And instead of x, I'm going to have a parentheses. And inside it'll say 60 minus y. Again, the reason I do that is just because then I don't really have to square something that's a binomial, because gross. So now I'm just going to go ahead and distribute this before I derive, so I don't have to do the product rule. So y squared times 60 minus y squared times y gives me that. And now I can actually find the derivative, because we're looking to maximize, right? So we need critical points and potentially endpoints. So in this case, that's going to be 120y minus 3y squared. And I'm thinking we're going to be able to factor this. Both of them have a y and both have a factor of 3. So I'm going to factor that out front, and that's going to leave me with 40 minus y. So then my, oh, you know what? I just said all this stuff about being in terms of x, and I'm using y's. So that's silly. Sorry about that. Okay, that just was going to bother me. All right, so in this case, my critical points would be at 0 or possibly 40. Okay, and this is where you need to always go back and check the context of the numbers again, make sure they're possible, because a lot of times we'll get critical points we actually have to throw out. So in this case, if I go back and look at the very first part of the problem, it says 2 positive numbers. So that means that y equals 0 really doesn't need to be considered. Y equals 40 is the only thing that I really can check. So to do that, I'm going to make my number line. I'm going to try checking 40 into this first derivative here. Okay, so that'll be p prime, and we're going to think about what that means for p. And if we're being accurate, I really could think of this guy down here as 0 since it can't be anything negative, just so I don't plug in something silly, right? So I'm really only plugging in numbers below 40 that are still positive. So if my test point is, let's say, 10, right, that's going to be a positive times a positive. So overall, that's going to be positive for the derivative. So that would be increasing for the function. And then if I plug in something greater than 40, like 50, that's going to be positive times negative, which means it'll be negative for the derivative, thus decreasing. And so we can see that we really are getting a maximization of the product, which is what it was asking for. And so we can draw this conclusion here, which again you have to state verbally since they're going to ignore any sort of number line you've drawn, and states it is a maximum since p prime changes from positive to negative. Okay, so now we can actually answer the question of what is the maximum product. So if y is 40, and we come over here, we can figure out that x is 60 minus 40, so x would be 20. And so if we actually found this mysterious product here of x times y squared, then it would be x of 20 times y squared, so 40 squared, which would give us a maximum product of 32,000. So that's the actual final answer, but your justification is just as important.